In this lesson, we are going to learn how to calculate for the equivalent resistance of circuits involving short circuit paths. Okay, so we are going to look at how to identify short circuit paths and then how they prevent current from flowing through resistors. So let's look at that. So from this circuit diagram that I have on the screen here, you'll see that we have a short circuit path here. Okay, so that's a short circuit path there. So this short circuit path is going to prevent current from flowing through this 3 ohms resistor here. Okay, this is because when the current from the source gets to this junction here, okay, it has two options, whether it will take this direction or it will take on this direction. By looking at this side here, because of this 3 ohms resistor here, which is offering resistance to this current, the current will not choose that direction because there's a resistance coming from that direction. And then looking at this path here, there's no resistance there, so the current will choose this path and then go back to the 5 ohms resistor. So at the end, you see that current didn't flow through the 3 ohms resistor. So therefore, we see that the 3 ohms resistor has been short circuited. So in this case, if you are asked to calculate for the effective resistance of this circuit, you are not going to add the 3 ohms resistor since it has been short circuited. So let's look at how this circuit is going to work. Okay, so I'm going to run a simulation for this circuit so that you see how the short circuit affects this circuit connection that we have here. Okay, so I'm running the simulation. So now you see that current flows through the 4 ohms resistor. Okay, and then it flows to the 5 ohms resistor also. Okay, you see these small yellow squares moving through the resistance. That's the current. Okay, so you see that it is flowing through the 4 ohms resistor and then the 5 ohms resistor, but it's not flowing through this 3 ohms resistor. This is because the 3 ohms resistor has been short circuited. So in this case, if you're asked to calculate for the effective resistance of this circuit, that would be R will be equal to 4 ohms plus 5 ohms, and that will be equal to 9 ohms. Since the 5 ohms and then the 4 ohms resistors will become series resistors, okay, because of this short circuit path here. So let's take another example. Okay, so let's look at this example here also. Okay, so we are going to look at how this short circuit path here will affect the resistors in this circuit. Okay, so what happens is that the current from the source, when it gets to this node here, it will move in this direction and then some also move in this direction. Okay, when it gets to this junction here also, since there's a resistor here and then there are resistors here also, it has no option down to split, okay, into two. So some will flow in this direction and then some also flow in this direction. Okay, but when the current gets to this node here, it also has two options, whether to move in this direction and then move in this direction also. Okay, but looking at this direction here, because of this resistor here, that's a 5 ohms resistor, the current will not move in this direction because it has a free path here where there's no resistance here. So the current will take this direction. Then when it gets to this node here also, it can move here and then it can move here also. But looking at this direction here, because of the 7 ohms resistor, it will not move in this direction but rather take this direction. So at the end, current will not flow through the 5 ohms and then the 7 ohms resistor. So you see that these two resistors has been short circuited. Okay, so if you want to calculate for the effective resistance of this circuit, you're not going to include the 5 ohms and then the 7 ohms resistor. So let's look at that. Now let's calculate the effective resistance of this circuit. So now the 5 ohms and then the 7 ohms resistors are not part of the circuit since they have been short circuited. So what we do now is that we are going to add the 3 ohms and then the 3.5 ohms resistors since they're in a series connection. So adding these two resistors will give you resistance of 6.5. That's 3 plus 3.5. That gives 6.5. Okay. So after that, these two resistors, that is 3 ohms and then the 3.5 ohm resistors, will be in a parallel connection with the 2 ohms and then the 4 ohms resistors. So at the end, you will have what? 4 resistors in the circuit, where what? 3 are in a parallel connection, then and then they are all in what? In a series connection with what? The 1 ohm. So let's look at the circuit now. So you have the 4 ohms here, then you have the 1 ohm here. Okay, this is the 4 ohm. Then this is the 1 ohm here. And then you have the 2 ohms here. And then you have what? The 6.5 ohms here. So then you see what we have what? 4 resistors in the circuit now. Okay, and then 3 of them are in what? In a parallel connection, which is the 4 ohms, the 2 ohms, and then the 6.5 ohms. And then they will all be in what? In series with what? The 1 ohms resistor. So let's look at what that means. So you are first of all going to calculate for the effective resistance for the resistors in what? In parallel. So that will be R will be equal to what? 1 over 4 plus 1 over 2 plus 1 over what? 6.5 all to the power what? Negative 1. So let's calculate for the value of what? The figures in the bracket. So that will be 1 over 4 plus 1 over 2 plus 1 over 6.5. That will be equal to 47 on 52. Okay, to the power of minus 1. And this will give us what? R to be equal to what? 52 on what? 47 ohms. That will be the effective resistance for the what? For the 4 ohms, the 2 ohms, and then the 6.5 ohm resistors, which are what? In the parallel connection. So then you have the circuit to be something like this. So here's the 52 on 47 ohms, and then here's the 1 ohm. So, okay, sorry, 1 ohm. Okay, so then the effective resistance will be what? 1 plus 52 on what? 47. Okay, and this give us what? R to be equal to what? 99 over what? 47 ohms. So that what? The effective resistance, that will be the effective resistance of what? The circuit. So now let's run the simulation for this circuit and then see how the short circuit affects the circuit. Okay, so now I'm running the simulation. So you see that what? From what you have here, current is not flowing through the 5 ohms and then the 7 ohms resistors. This is because of what? The short circuit path here. So that was why we didn't add the 5 ohms and then the 7 ohms when we were solving for the equivalent resistance of what? This circuit. So that's how the short circuit path here affects what? This circuit. Let's take the last example. Okay, so I have this example here also. Okay, so let's look at how you're going to calculate for the effective resistance of what? This circuit. So when current is flowing from this voltage source here, okay, and then it gets to this node here, it can branch in this direction and then it can branch in this direction also. Okay, but I see that when branch in this direction, there is a 4 ohms resistor here, and then in this direction also there is what? This 15 ohms resistor here. Okay, and looking at this path here, there is no element there. Okay, so that's what the short circuit path. So the current, we'll see that there's a resistance from both the left side and then the right side, and then there's no resistance what from this path here. So it will take what? The middle direction. Okay, so the current will flow in this direction, therefore leaving the 4 ohms and then the 15 ohms. So at the end, what? No current will flow through the 4 ohms and then the 15 ohms resistance. So you will see that what? These two resistors has been short circuited. So then you have the circuit to be something like this. So we only have what? The 3 ohms resistor in the circuit now, since the 4 and then the 15 ohms has been short circuited. So in this case, the effective resistance will be what? 3 ohms. That's how short circuits affect circuit, okay, when you are doing what calculation. So you have to take note of what short circuit anytime you're calculating for effective resistance of what circuit. So now let's look at the simulation for this circuit also. So when I run the simulation, you see that what current is now flowing through the 4 ohms and then the 15 ohms resistor. So this means that what they had what short circuited. So that was the reason why what we didn't include these two resistors when we're calculating for the effective resistance of what of the circuit. So you see that what when I take out this short circuit path, okay, from this circuit, current will start flowing through the 4 ohms and then the 15 ohms resistors. Okay, so you can see that what now current is flowing through it, the 4 ohms and then the 15 ohms resistor because what the short circuit path is no more there again. But when I bring it back, current will stop flowing through the 4 ohms and then the 15 ohms resistors.